Hi everyone, welcome. In this video, I'm going to provide an example on bottleneck analysis and the theory of constraints. And I chose to provide a simple example on a hypothetical question where there's a Tim Hortons drive-thru. If you do not know what Tim Hortons is, maybe Tim Hortons is not doing its job to advertise itself. So this is not an advertisement. I'm not getting paid for this. Anyhow, let's say there are two order stations for this drive-thru, and the cars line up and they order their coffee and their donuts, etc. And then they could just two cars at the same time can line up and they can make an order, and then they just move on and just go into a payment station and they pay their payment due, and then they go to pickup window and then they pick up their order and they leave. So when they make the order, then the shop prepares the order, and then the pickup window takes an additional 50 seconds. It's not the prep time. So this is the time where they go to the pickup window, and it takes about 15 seconds for the pickup window to provide the order. It may take less than that, but let's say this is on average 50 seconds, and it's a hypothetical example. Now, because the order station there's order station 1 and there's order station 2, these are parallel order stations. A customer does not visit both order stations. The customer only visits one of them, but then the customer goes into the payment station and the pickup window. That means every customer spends 80 plus 70 plus 50 seconds in this drive-thru. And the bottleneck time is the time for the bottleneck for this process. And here the bottleneck, we have to just identify which station is the bottleneck station for this process. Now if I take a look at here, the order station takes a longer time, but there are two order stations, and because each one takes 80 seconds, the order station is capable of sending one customer every 40 seconds. So two customers every 80 seconds to the payment station. And that means the order station has the time of about 40 seconds. The 40 seconds is not the time that the customer spends there. This 40 seconds is the capacity of the order station. So one customer every 40 seconds, two customers every 80 seconds. And then, so that is 40 seconds. And the payment station is 70 seconds, and the pickup window is 50 seconds. That means this process, after the first customer, is going to be able to handle one customer every 70 seconds, because this is the longest of the station times. So the bottleneck time, and sometimes you see this as a cycle time, is 70 seconds, and the bottleneck activity, the bottleneck station, is the payment station. So we will just put that in here. We will say that this is the bottleneck. So this is 70 seconds is the time to process one order, or you could just think it in this way. If you wait at the end of this assembly line, you will see one customer coming out of this assembly line, coming out of this Tim Hortons drive-thru every 70 seconds. Okay, so now what we want to do is we want to look at the capacity of this process, and the capacity is nothing but just 1 over the bottleneck time, 1 over the cycle time. So this is saying that we will have 1 over 70 customers every second processed in this drive-thru system. So this is customers every second. Then I can also take a look at that number and multiply that number times 60, and that will give me the customers every minute times another 60, the customers every hour. So this process, this drive-through is capable of processing 51.42 customers every hour, but this is only after it's up and running. What does it mean is that the first customer is going to take the throughput time. The first customer is going to go through this process 80, 70, and 50. So the first customer will be out of this process, will exit from this process in 200 seconds. But then the second customer is going to exit from this process in 70 seconds after the end of the first customer. So this is going to happen 70 seconds after the first customer. So this will be 200 plus 70. And I could just put that 200 there and multiply, add that value up. And the third customer is going to be 70 seconds after the second customer. So you will see one customer coming out of this process every 70 seconds after the first customer. So that's why sometimes you will see the statement saying that after the process is up and running, meaning that the process becomes stable. So the first customer goes out, and then the process will produce one product, which is a satisfied customer every 70 seconds. But now if this 51 customers is not sufficient enough for the business, and let's say there are more customers coming in than the customers can be served. So the capacity is 51 customers every hour, but let's say in the morning they get 60 customers or 70 customers every hour. So how are they going to be able to manage that and just maybe increase the capacity of the system? Are they going to put one more order station? Are they going to put one more payment station or a pickup window? Now if you take a look at the situation here, you realize that the bottleneck is the payment station. So what we have to do is we have to maybe add one more payment station. So I'm going to just do this. I'll maybe put one more payment station here. So if I put one more payment station, what's going to happen is whichever payment station is available, then the customers will choose to go to that payment station. So the customers may go from order station 1 to payment station 2, or order station to the payment station 2, or order station to the payment station 1, or order station 1 to payment station 1. So it's kind of hard to say that payment station, order station, etc. But let me just put that arrow in here. So we have those arrows, and now what's going to happen is first available payment station, the customer may just jump into that. Let's assume that. Now if we have two payment stations now, we just put also an arrow from payment station 2 to the pickup window. So how are we going to be able to calculate the capacity of this process? Now if there are two payment stations, what's going to happen is the payment stations are going to be able to process 2 customers every 70 seconds. So the payment station time is technically turns into the cycle time for the payment station is 35 seconds. And the order station is 40 seconds because there are 2 order stations and 2 payment stations, and the pickup window happens to be then only 1, that's 50 seconds. And if I consider this 80 divided by 2, there are 2 stations here, 40, and this is 35, and this is 50. That means if I have 2 payment stations, then the first customer will be out in 200 seconds. Every customer is going to take 200 seconds, but the second customer will be out in 250th second. The third one will be out 300, 350, etc. So the bottleneck time will turn into 50 seconds only. And in that case, the capacity will just jump to 72 customers per hour, and our new bottleneck is the pickup window. So I hope that you understand the idea behind the bottlenecks and parallel stations, and the throughput time doesn't change when you are adding parallel stations, because the products or the customers do not visit every parallel station, they only visit one of them. So in order to calculate the throughput time, you always look at the longest path. But the bottleneck time, in order to calculate the bottleneck time, you have to look at the parallel stations and find their bottleneck times by dividing their durations by the number of stations, and then you determine again the longest time, which station takes the longest time, and that would become the bottleneck station. So in here, let's say if they want more than 72 customers, then the third option is going to be then pick up one more pickup window maybe, then that is going to decrease the pickup time to 25 seconds, and the pickup bottleneck time 25 seconds. Then this is 35 seconds and this is 40 seconds. Then the order station becomes a bottleneck again, but then the capacity will just increase a little bit more. I hope it makes sense, and thanks for watching.